String time crystals. Presentation for the annual Time Waiver and Healy Scientific Advisory Board Conference, September 2024. By Dr. Hovdank Tadeus. String time crystals and Bose-Einstein condensates as a new state of matter involves three parts: holistic string time crystals theory, string time Bose-Einstein condensates matter, and string time crystals and Bose-Einstein condensate for therapeutic application in quantum feedback. Bose-Einstein condensates and time crystals. Both BECS and time crystals exhibit quantum coherence, BEC in space and time crystals in time. The control over quantum states and the ability to maintain coherence make BECS a suitable platform for studying time crystals. Both BECS and time crystals involve fundamental quantum properties, such as entanglement, superposition, and non-local correlations, making them valuable for exploring quantum mechanics and potential applications in quantum computing and other technologies. Modeling with string theory. Vibrational modes. In string theory, particles are viewed as vibrating strings. Their vibrational modes determine physical properties. Application. Biological systems can be modeled as strings with specific vibrational modes corresponding to their health state. Higher dimensions. Use string theory's concept of extra dimensions to understand hidden factors affecting health, visualizing the body's quantum information field in multidimensional space. Bosonic string theory. Bosonic string theory offers a compelling framework for understanding time crystals, particularly when studied in conjunction with Bose-Einstein condensates BECS. Bosonic string theory provides a simplified and directly relevant framework for studying the bosonic nature of BECS and time crystals, making it particularly advantageous for exploring particles in BEC that condense into a single quantum state, enhancing quantum coherence and allowing for macroscopic quantum phenomena. String mode and time crystals. The concept of string modes and time crystals can intersect in the idea that the periodic vibrations of strings could theoretically be linked to the temporal oscillations seen in time crystals. If a quantum system like a Bose-Einstein condensate could enhance string vibrations, these vibrations could manifest as time crystalline behavior, where the oscillations are synchronized and maintained over time due to the system's quantum coherence. This suggests a potential framework where string theory and the physics of time crystals converge, offering insights into the nature of time, matter, and quantum states. Bosonic string theory. Bosonic string theory offers a compelling framework for understanding time crystals, particularly when studied in conjunction with Bose-Einstein condensates BECS. Bosonic string theory provides a simplified and directly relevant framework for studying the bosonic nature of BECS and time crystals, making it particularly advantageous for exploring particles in BEC that condense into a single quantum state, enhancing quantum coherence and allowing for macroscopic quantum phenomena. Space-time symmetry and relativity. Connections between space-time symmetry (STS) and biological chirality propose that the inherent properties of elementary particles and fundamental forces shape the chirality observed in biological molecules. STS and spacetime relativity (STR) persist across all nature's scales, from subatomic particles to galactic structures, and their influence on the emergence and maintenance of biomolecular chirality. Standard model and string theory highlights the bidirectional pathways through which physical laws impact biological matter, leading to the prevalent chirality seen in biomolecules like DNA and proteins. These principles extend to biological functions and cognitive processes. This bridge between physics and biology, proposing that the symmetry and asymmetry in spacetime are fundamental determinants of the chiral properties essential for life. Conformal field theory and time crystals. Conformal field theory, particularly in its Floquet-driven form, provides a robust framework for studying time crystals by leveraging its tools for understanding symmetry, periodicity, and non-equilibrium dynamics. The adaptation of CFTs to include non-equilibrium conditions, like periodic driving, offers a theoretical approach to capturing the unique properties of time crystals, including their stability, coherence, and response to external driving. 2D CFT tools for time crystals. Many concepts from 2D CFT, including the modular Hamiltonian, stress energy tensor, and symmetry generators in translation, rotation and scaling symmetries, offer a rich framework that could be adapted to study time crystals. Chiral conformal field theory. Time crystals and chiral conformal field theory offer intriguing theoretical frameworks that could support and explain chirality in biological systems. By leveraging the principles of symmetry breaking, coherence, and directional asymmetry, these concepts could help model how biological systems maintain chirality over time, possibly through time crystalline behaviors or chiral quantum states. This intersection opens up new avenues for research into the quantum nature of life and the fundamental principles that govern biological organization and function. The tools and ideas from Liouville CFT, such as dealing with exponential potentials, continuous spectra, and non-equilibrium behaviors, could be adapted or extended to provide a deeper theoretical understanding of time crystals, particularly in understanding how they maintain coherence and stability in a non-equilibrium state. The space of states, or the spectrum of a CFT, is the set of all possible quantum states that the theory can describe. This space is a representation of the product of the two Virasoro algebras L(n) for holomorphic left-moving and L(n) anti-holomorphic right-moving part of the theory, characterized by delta, left conformal dimension, delta bar, right conformal dimension, delta plus delta bar, total conformal dimension or the energy, delta delta bar, conformal spin. Photonic time crystals. Photonic time crystals (PTCs) are spatially homogeneous media whose electromagnetic susceptibility varies periodically in time, causing temporal reflections and refractions for any wave propagating within the medium. Photon-phonon time crystals. In a phonon-photon time crystal, both light photons and lattice vibrations phonons are influenced by a time periodic structure. The interactions between photons and phonons can lead to non-reciprocal effects and other complex behaviors, as described in the document regarding the photonic Aharonov-Bohm effect, where both phonons and photons exhibit time crystal-like behavior. Photonic time crystals as beam splitter. A traditional beam splitter material transformed into a photonic time crystals PTC to act as a regular beam splitter with additional variability due to its time-changing refractive index. When a photon encounters this PTC beam splitter, its behavior would be influenced by both the conventional splitting properties and the dynamic modulation of the refractive index, offering enhanced functionality for quantum randomness. Time crystals and M-theory hybrid model. The time crystals and M-theory hybrid model merges the unique time periodic properties of time crystals with the multidimensional, quantum framework of M-theory. This model provides novel insights into quantum coherence, symmetry breaking, and the fundamental nature of reality across both time and multiple spatial dimensions. A time crystals and M-theory hybrid explores how time crystals' properties relate to the dynamics of these higher dimensional branes. This model examines how time periodic behaviors manifest in the context of higher dimensional spaces and brane interactions, providing a more extensive framework to explore multidimensional oscillations and non-equilibrium quantum states. Higher dimensional branes and time crystals. M-theory introduces the concept of branes, which are higher dimensional objects extending beyond the one-dimensional strings of traditional string theory. By integrating time crystals into M-theory, researchers can explore how these branes might exhibit periodic behavior in time, similar to the way atoms in time crystals oscillate in a repeating pattern. This suggests that branes could form not just spatial structures but also temporal patterns, providing new insights into the fabric of space-time. D-brane time crystals beam splitter. Photonic time crystals PTC within a beam splitter acts like a brane whose time-varying properties dynamically influence the paths of photons, akin to how strings in M-theory are affected by the branes they are attached to. The PTC's changing refractive index represents the oscillations of the brane, while the photons act as strings that are modulated by these oscillations, leading to quantum variable optical outcomes. Thank you all for your time and interest.